supposed to finish in a couple of years. So thank you, Clara. You can go ahead.
Okay, thank you. So hi, my name is Clara Dehman and I am a PhD student in Magnesia Group. As Mar mentioned, I work under the supervision of Nandaria and Daniele Vigano, and I also work with close collaboration with Professor Jose Antonio Pons in Alicante and with Stefano Accenzi. Today I'm gonna present this new code to study a new finite volume code for the magnetic evolution in 3 dimensions. This code is designed to study magnetothermal evolution in neutron star. Last week we saw that Stefano Accenzi has presented the thermal part of this code, and today I'm gonna focus on the magnetic part since it's my main PhD project. Okay, so when speaking about magnetothermal evolution in a neutron star, it's important to keep in mind the interior structure of a neutron star. So for this reason, basically, I will spend some time speaking about the interior structure of a neutron star. And then I will also speak a bit about some observational properties of a neutron star, because this is what motivates us to study the magnetothermal evolution in neutron stars. So neutron stars, they are this compact and extreme object. They have the strongest field in the universe. They have a mass between 1 and 2 solar mass and a radius between 10 and 13 kilometer. And one can distinguish several layers in the interior structure of a neutron star. So what we see here is basically a slice of a neutron star, and the layer that we distinguish are basically the envelope and the atmosphere in the very outer layer of the neutron star. Then the envelope basically is an ocean of 100 meter, and it's composed out of heavy element, and also it can be composed out of light element if the neutron star accreted a lot. Then we have the crust of a neutron star. Basically, the crust of a neutron star is about 1 kilometer radius, and one can distinguish two regions in the crust of a neutron star. The outer crust, which is formed out of a lattice, it's a lattice of neutron-rich nuclei, and we have a gas of relativistic free electrons. Then the more we go toward the inner layer of the neutron star, the density increases, and the neutrons start dripping from the neutron-rich nuclei. So this is when the neutrons start dripping from the neutron-rich nuclei is when we have the inner crust starting. And the inner crust, so it's composed out of this lattice of a neutron-rich nuclei, out of the dripped neutron, which is a gas, and out of the relativistic electrons. And then one can distinguish also the pasta layer in the very interior region of the inner crust. This pasta layer is formed due to the competition between the Coulomb force and the strong force in our system, and it's characterized by being a highly resistive layer. Then we have the core of a neutron star. So basically the core of a neutron star accounts to most of the volume, the radius, and also the mass of the neutron star. It's a uniform nuclear matter that's composed out of neutron, proton, electron, and likely also muon, if the chemical potential of electron allows for the formation of muon. And then in the very inner region of the star, we have this unknown ultra-dense region, where neutron and proton there is a hypothesis that neutron and proton can form hyperon, they can split down into quarks, or they can even remain neutron and protons. Now outside the neutron star we have its magnetosphere. The magnetosphere of a neutron star play a very important role in explaining several observational properties. So let's just describe a bit the observational properties of a neutron star. So neutron stars, they come in different flavor, and we classify them according to their primary source of energy or their energy reservoir that power their emission. Basically these neutron stars, some of them, their emission is powered due to the dissipation of a super strong magnetic field, which is the case of Magnetar. Some other are powered due to the loss of rotational energy, like the rotation radio pulsar. Some other are powered due to the internal heating, which is the case of XDIM, X-ray dim isolate XDIMs, X-ray dim isolated neutron star, or the CCO, central compact object. And then we have the binary. So the binary, since when we are in a binary system, there is accretion between these two objects in the binary system, and this accretion power the emission that we observe from a magnetar, from these objects. Now we like to classify Magnetar in this PP dot diagram. So here we have the spin period of this object and we have their period derivative. Why? Because in this diagram one can see that different classes of a neutron star, they cluster in different region of this diagram. So for instance, we can see the Magnetar in the top right side or top right corner of this diagram. Then they are followed by the X-DINs. If we move diagonally, we have the bulk of population of isolated neutron star, which are the rotation radio pulsar. Then we have also three central compact object. Yeah. In reality, we know about 12 of these objects, but we know only 3 of them with measured period and period derivative. And in the bottom left corner, we have the binary system. Now, how do they measure the magnetic field in a neutron star? Basically, the main observable are the period and the period derivative. From the period and period derivative, one can have an idea on the characteristic age of this object, which is just an approximation of its real age. But moreover, in order to determine the value of the magnetic field of this object, one have to assume the magnetic dipole breaking model, where they managed to determine the value of the dipolar component of the magnetic field at the pole of this object by considering this formula that can be written in terms of the period and the period derivative. And since we are studying here the magnetic evolution in neutron star, let's focus a bit more on the characteristic of this highly magnetized object, the observational properties of this highly magnetized object. So basically we saw that this highly magnetized object, they are powered due to the dissipation of very strong magnetic field of the order of 10 to 14 to 10 to 15 Gauss. They are young object, so they have an age below 10 kilo-year. They are slow rotators, so they have a spin period between 1 and 12 seconds. They mostly emit an X-ray, so most of them are quite a radio. I think we know about 5 or 6 of them that are active in radio, and their X-ray luminosity is higher than the X-ray luminosity of other classes of a neutron star, and they are characterized by 2 types of emission, the flaring activity and the outburst emission. The flaring activity is a short time scale activity. It's of the order of second or minute. It can be a giant flare, which are these very rare events. We only know 3 of them, and they are extremely powerful events. So they are the second in term of luminosity to supernova explosion. Then there is the intermediate bursts, which are intermediate between giant flare and short bursts. And there is the short bursts, which are very short event, less than a second, and it's thanks to a short burst that they detect a new magnetar. Because a short burst, it announces that a magnetar has entered an active phase, or the so-called outburst. So what we have is the following. We have the magnetar, or these highly magnetized objects that are out in the sky, and basically when they are not in the active phase, we cannot observe them due to the limitation in our satellite, most probably. And so what happens is that when the magnetar enter in the active state, this persistent X-ray luminosity of a magnetar, it increases by 1 to 3 orders of magnitude. The increase in this luminosity, it happens very fast, or less than 2 days, and then it remains high, where at this level we can observe the magnetar. So it remains high, and then it decays back to the quiescent level on a time scale ranging from months to year. And once it arrives to the quiescent level, the magnetar is again not observed. Now the question is, what is the physics behind this burst and outburst, or this magnetar activity? So we saw that these objects are slow rotator, so their emission cannot be powered due to the loss of rotational energy, and we think that their emission is powered due to the dissipation of a super strong magnetic field, which power this outburst and burst event that we observe from this object. So now we understand why we need to study the magnetic evolution in this object in order to be able to describe the observational property. But we want to understand why we want to go to 3 dimensions, since in our group we have already a 2D magnetothermal code, where we have the code coupled together and we have some real calculation of the microphysics. Now we need to go to 3D. Basically because we know that a realistic topology of the magnetic field is a complex and non-axisymmetric topology, so we need to go to 3D in order to be able to describe such a topology. Then we also know that the magnetic evolution is expected to give rise to 3D modes, so we need a 3D code in order to study this 3D mode. And finally, a 3D magnetic evolution lead to the formation of hotspot on the stellar surface, as we saw with Stefano last week. And these hotspots are basically the ones that are formed, for instance, from the outburst event. And in order to describe this hotspot, we need the 3D magnetothermal code. So now let's move on in order to describe the 3D magnetic code. To build this 3D magnetic code, we have considered the so-called cubed sphere formalism. So what is this formalism and why did we use it? Now in the 2D code, the 2D magnetothermal code, we use the normal spherical coordinates. They use the normal spherical coordinates, the radial and the two angular coordinate theta and phi. When we go to 3D, there is the well-known problem, which is the axis singularity problem. What does it mean? It means that along the axis, you have some, for example, some component of the magnetic field, like the B phi component of the magnetic field is ill-defined. You cannot define it, simply speaking. And then you have also some geometrical element, like the area, for example. They go to 0 at the axis. So let's say you are doing some evolution, you are dividing with some area, you get none, you get infinity, and you cannot follow any evolution. So this problem basically need to be solved. It's not a new problem. It's a well-known problem in atmosphere physics and the GR code and geophysics and so on. And what people consider in general is this cubed sphere formalism. In this cube, in order to understand this cubed sphere formalism, let's imagine that we have a cube. The cube it has 6 surfaces, and we start inflating our cube such that the 6 surfaces of the cube they cover the spherical surface. Now this spherical surface, it can be split into 6 identical patches, as we see here. We need 4 of these patches to cover the equatorial belt, and 1 patch in the north and 1 patch in the south. Each of these patches now it have its own coordinate system, meaning that this is patch number 1, it have its 2 angular coordinate system, patch number 2 it have another coordinate system, and they are all identical patches. Now the desirable feature about such a coordinate is that the radial coordinate is the same as a spherical, so this is something good. The other one is that it solves the axis singularity problem. Now there is always a cost to pay. Basically, the cost to pay is that your metric is non-orthogonal, which means that your grid is non-orthogonal, and so there is this off-diagonal term, and that means that any mathematical operation you want to do now is more complex and have some extra term to deal with. The other cost to pay is that you have to let these patches speak together. You have to connect the patches together, which was not something pretty simple. Okay, so let's describe the magnetic evolution, the approximation for the magnetic evolution used in this code. So when we were speaking about the interior structure of a neutron star, we saw that the interior of a neutron star, there is different species like neutron, proton, electron, muon, and so on. And if each of these species it has its own hydrodynamical velocity. So in order to understand better our problem, let's move like layer by layer. So let's go to the crust. We have the solid crust. We know that in the solid crust we have these lattice of neutron-rich nuclei that have restricted mobility, so they don't move, and we don't need to worry about them when describing the magnetic evolution. Then we also saw that there is this gas of a free neutron, but neutrons do not carry any current, so we also do not need to worry about them in the magnetic evolution. And we saw that there is the electron. The electrons are the main charge carrier in the crust, and the conduction is governed by electron in the crust. Now when we go to the core, instead the core is like there was several species. There is the neutron, the proton, the electron, the muon. We know that neutron and proton can be superfluid, superconductive. We know that the ambipolar diffusion will play an important role. So the physics of the core in reality is less known. And at this level of our approximation, or at this level of our study, we are restricting our field to the crust, and we are doing the evolution in the crust. So our induction equation is then simplified to the electron magnetohydrodynamic induction equation, where we have here the ohmic dissipative term, which means that our magnetic field dissipates in time. Eta is the magnetic resistivity. The highest the eta, the more our field dissipates. This is the whole drift term. It's the term that's responsible on drifting the magnetic field line toward the inner layer where there is this pasta layer. And also it's responsible of forming some little small scale structure in our topology of the magnetic field. Now, we have this equation as a continuous equation. In order to solve this equation numerically, we need to discretize it. So basically, we discretize it in terms of these cubed sphere coordinates. So we see here kind of 4 dimensions. What are they? So we have one radial dimension, the 2 angular dimension we spoke about, but then we also have some patch dependence, which is not like a dimension, but it's more like a dependence, because each of these patch has its own coordinate system. To solve this equation, we consider an explicit scheme. An explicit scheme, it means that you solve the state of your system at time t1, the new time, only using the state of the system at time t0, the current time. And then the question comes is, where does the thermal evolution play an important role in this equation? It plays an important role in this magnetic resistivity, where this parameter is very, very sensitive to the temperature evolution. The higher temperature, the higher is the magnetic resistivity, and more the field dissipates. And that tells about the importance of having the magnetothermal code coupled together with real calculation of the microphysics in order to provide real results. Now, to solve this equation, we need to follow some logic. So basically, the first thing we need to do is to initialize our system and to give input. So basically, we have been speaking about this cubed sphere grid, so we need to construct this cubed sphere grid. So we need to construct our grid. And at this level of the development of the code, since we are not yet using any realistic microphysics, we basically are not using any equation of state to construct the structure of the star. And that means that what we have for the moment is like a metallic ball, not more. Then we need to initialize our magnetic field. And to solve this equation, we see that we need this eta and fh, the magnetic resistivity and the Hall prefactor. So at this level of the development of the code, we are just using some analytical microphysics. We are not doing the real calculation. Then we see that we need the current to solve this equation. So we need to calculate the current. And in order to calculate the current, we use Stokes theorem in cubed sphere. Then we need to calculate the electric field. We do calculate the electric field. And then a very important thing to do is to understand how correct are our results. In order to understand how correct our result, we need to do some magnetic analysis, which basically what we do is that we study the energy balance in our system. The total energy in our system should be conserved. And we also study the divergence of the magnetic field. So our magnetic field should be divergence free. Then in order to solve this equation, we need to consider some time step, magnetic time step. We choose the magnetic time step in order to advance in time, and we do some time advance method in order to calculate the magnetic field at the new time. With our time advance method is the Runge-Kutta-4 advanced method. And now we update the magnetic field, and we have the magnetic field at the new time. Once we have that, we basically need to apply boundary condition. So we have basically our system, our crust, where we are doing the evolution, and we have the surface of the star is where we have to apply the boundary condition, and also at the crust core interface is where we also have to apply the magnetic boundary condition. Then there is the extra cost to pay, which is connecting these patches with each other. That it's very technical, and I will not speak about during this talk. And once all of that is done, now we update our time. So we are like at time t1, for example, instead of time t0. And we repeat the same until reaching to the final time. For example, we want to solve until 1000 years. We repeat the same until reaching 1000 years, and then we stop. Now, to do this evolution, several pieces need to be worked carefully. One of them is the initial topology of the magnetic field that should be divergence free. The other is the magnetic boundary condition. And I will also spend a bit of time speaking, like just a few words about the analytical microphysics that's considered in this work. Okay, so let's start with the divergence of the magnetic field. the only requirement is that our magnetic field should be divergence free, and the way to do that is to construct our magnetic field starting from vector potential, where basically you can write this magnetic field in terms of poloidal and toroidal decomposition. And in that case, you can write your magnetic field in terms of these two scalar functions. These two scalar functions, they can be written as a sum of spherical harmonics and some radial function. These spherical harmonics, they describe the angular part of our topology. Now, how to define a specific topology? Let's say you want a dipole, for example. In order to define a dipole, you simply choose L equal 1, M equal to 0 if it's axisymmetric, plus or minus 1 if it's non-axisymmetric. You want a quadrupole, the same, you choose L equal 2. But what is convenient about such a way of defining our initial field is that you can easily construct a multipolar topology by just simply summing different spherical harmonics, because you know that your magnetic field, the realistic magnetic field, is a neutron star. It's probably a multipolar complex field. Now, so what we are free basically to choose our spherical harmonics and to consider the topology we want, but we are more restricted in the choice of the radial function. For this radial function, they should be consistent with the magnetic boundary condition. And basically, to do so and to be consistent with the magnetic boundary condition, I'm using for the poloidal radial function this expression that's derived in Aguilera, but for the dipole only. So for the dipole only, I'm using this expression. Whereas for the toroidal radial function and for the higher multiple poloidal one, I'm confining them inside the crust. So basically, at both boundaries, they go to 0, and like that, we are consistent with our magnetic boundary condition. Now, once we know these two pieces, now we know our scalar function. To determine our magnetic field, we apply the Karl operator in cubed sphere coordinate, and we construct our magnetic field in cubed sphere coordinate, which means that we have now a divergence-free magnetic field, since we are constructing our magnetic field in this following way, and it's also in cubed sphere coordinate, which means that it has no axis singularity problem. Okay, let's just here, I will just mention a bit about what are the analytical profile used in this work. We have to fit or we have to give two microphysical property expression, let's say. One is the Hall prefactor and the other is the magnetic resistivity. For the Hall prefactor, we have this fit that have been determined by Daniele in his 2021 paper. It's a fit of the realistic microphysics of the 2D magnetothermal code. So we use the same fit, and like that we are kind of providing some realistic result by using this fit. Now for the magnetic resistivity, things are a bit more complicated because this parameter is very sensitive to the temperature evolution. And so what I am providing here is some analytical expression that show some higher magnetic resistivity in the outer crust and in the pasta layer. And this analytical profile is a bit comparable to the realistic, the profile of the microphysics of the eta parameter of the microphysics of the 2D code at a temperature of 10 to 8 Kelvin. Now, once we know FH and eta, and we also know the magnetic field, we can define the so-called Reynolds magnetic number. This Reynolds magnetic number it tells about the relative importance of the Hall term and the ohmic term in our induction equation. If it's order of 1 or higher, then it's the Hall term that dominates. If less, it's the ohmic term that dominates. Okay, last piece we want to build is the magnetic boundary condition. Let's start with the inner boundary condition. We are considering that our magnetic field is confined to the crust, and the requirement to construct such a field is that the radial component of your magnetic field should go to 0 at the crust core interface, and also the tangential component of the electric field should go to 0 at the crust core interface. To implement such a condition is very easy. You just set 0, this quantity, at the crust core interface. However, now there is a problem that is there, and this is a well-known problem when you consider a full grid. It's called the odd-even decoupling problem. So what is this odd-even decoupling problem? This odd-even decoupling problem is this problem that appear and it's basically when you are considering full grid. And in this problem, basically your odd family and your even family of grid cells, they are kind of decoupled together, so they don't speak together. So let's understand it better looking at this very simplified grid. Let's say I want to calculate the current at this cell, the one that's in red, it's G22. I need the magnetic field at these four points, which I am putting my mouse on them. Then let's say I want to calculate the current at cell number 4. I also need the magnetic field at these 4 points. And what we see is that these two cells, they are basically sharing information about the magnetic field at cell number 3. Now, if we go and we want to calculate the current at cell number 3, we see that cell number 3 is not sharing any information about the magnetic field with cell number 2 or with cell number 4. So they are touched, they are kind of two solutions. And then what we have to do in a simplified way is to apply some mathematical tricks at the boundary condition, so that we applied at the inner boundary condition and also at the outer boundary condition, in order to connect these two families together. Once we do that, so we see here it's a b theta profile of the magnetic field as a function of radius at 1000 years. So in solid line we have the odd-even decoupling, so we are not yet applying any solution for the odd-even decoupling, and in dashed line we apply the solution of the odd-even decoupling, and we see how our result is, they are very smooth and coupled together. Okay, last piece, and then we can move to the result section. The potential boundary condition. So you are in this star, and we know that outside our neutron star we have the magnetosphere that exists there, but at this level we are not coupling our code with any magnetosphere, and what we are considering is that there is no current that circulates outside our star. So under this assumption, it's called the potential boundary condition. The magnetic field can be written as the gradient of this magnetostatic potential. The magnetostatic potential is just a scalar function that can be defined in terms of the spherical harmonics, some radial function, and this BML. These are the weights of the multiple, and we need to determine this weight in order to construct our boundary condition. So to do that, what do we have? What we know is the radial component of the magnetic field at the surface of our star. And what we aim at constructing is a two-angular component of the magnetic field at the surface of the star and also one cell above the surface of the star. And to do that, we need to find our weights, the weights of the multiple. It's very simple. You have your radial component of the magnetic field, and you know it. And you know at the surface of the star, you can write your magnetic field in terms of the radial derivative of this magnetostatic potential. And then you have the following expression. These go to 1 at the surface, and then you apply some spherical harmonics property, and you can find your weights, the weights of the multiple. Once you find your weight, you can easily construct your two angular component of the magnetic field, since they are simply the theta and phi derivative of this magnetostatic potential. Now, having all of this derived and implemented, we can start testing. I will show you in total 3 tests, or 2 tests, or 1 test and 2 simulation. The first test is the ohmic dissipative test. So in this test, I am basically testing the ohmic term of the induction equation only. And for this test, luckily, we have an analytical solution, which means that we have a numerical solution that's obtained in our code, doing the evolution in the code. We have an analytical solution, and we can compare the two solutions in order to understand how correct are our results. So in this Bessel test, I consider force-free solution, which means that your current can be written as a function of the magnetic field. And in this test, this alpha and eta are constant. So they can just go out, and your induction equation is simplified to the following form. And this basically is translated that, or it can be expressed that the magnetic field at a given time decay exponentially as a function of minus t over tau d. Tau d is the diffusion time scale. And a possible family of solutions that satisfy the above relation is this initial topology. where alpha is a wave number in length unit, and the higher your alpha, the more you have curvature in your field. What I am showing here is the phi component of your magnetic field as a function of radius, so it's a radial profile, and it's shown at a given angle in the star at different diffusion timescale. Basically, the solid line, they correspond to the analytical result, and the crosses on the top, they correspond to the analytical result. So the solid line to the numerical result, and the crosses on the top to the analytical result. And we see that both analytical and numerical result, they perfectly overlap. Moreover, we see that around 4 diffusion timescale, the magnetic field almost completely dissipated. Then, if we, in order to understand how comparable are the analytical and the numerical result, it's better to study the L2 error. So here I am plotting the L2 absolute error for the 3 components of the magnetic field, the radial component and the 2 angular component. We see that the 2 angular components are showing higher L2 error, and that's probably due to the patchy grid because of these patches that we have in our grid. But what's important that around 1 diffusion timescale, this error saturates and it's not growing in time. The same for the radial component, maybe around 2 diffusion timescale. So we think that this test has passed successfully. And we think that now our ohmic term, or the ohmic term of our induction equation, is properly working and giving the right result. So now we have to move on in order to study the whole drift term of our induction equation, which is the nonlinear term and the more difficult term to test. Now, to test the whole drift term of our induction equation, we don't know any analytical solution. So because this term is complex and there is no analytical solution for it. So, but a way to test it, since we already have a 2D code that has been developed in the last decade, basically by Jose and Daniele, we trust the result of the 2D code. And what we can do is to do a comparison between the 2D and the 3D code. So basically, to do that, we have to simplify the 2D code. So I froze the temperature in the 2D code to have only magnetic evolution. And I also basically simplified the microphysics of the 2D code and considered the same analytical microphysics that I am considering in the 3D code. And in this comparison, we are restricted to axisymmetric topology, which means m equal to 0, because the 2D code can only study m equal to axisymmetric topology. And what I am showing here is, what I have considered as initial topology is a poloidal field. That's a dipolar field, and it have a 10 to 14 Gauss in initial intensity. I have a toroidal field that was a sum of quadrupole plus octupole and of 10 to 15 Gauss. I also adapted the same crustal shell, the same size of the crustal shell, that's as following. And I ran a simulation up to 100 kiloyear. Basically, what I am showing here is the energy as a function of time. The solid line, they correspond to the result of the 3D code, and the dashed line, they correspond to the result of the 2D code. In black, we have the energy balance. The red is the joule dissipation, the Poynting flux in yellow, and basically in blue the magnetic energy. We see that both code the result of both code are very comparable, and we also see that both code they show that the energy balance is conserved, it's a constant, which is something good. The other thing we wanted to check is the divergence of the magnetic field. So since we are doing this numerical evolution, we cannot have this perfect divergence of the magnetic field is equal to 0, even if we construct our field in such a way, because there is this numerical contribution, this machinery error. So basically, what we have to do is that we have to compare the divergence of the magnetic field with some quantity of the same unit, which in this case is G2 of the star. They have both the same unit. And what I am showing in blue is the G2 of the star for both code that is perfectly overlapping. And then there is also the divergence in black line. The solid line is the 3D code, the dashed line is the 2D code. So we see that the divergence of the magnetic field in both codes is orders of magnitude lower than the G2 of the star, which means that both codes are conserving well the divergence of the magnetic field. Moreover, we see that the divergence of the magnetic field in the 3D code is saturated and not growing in time. So this is what tell us that the 3D code is doing well. Here I'm showing some radial profile of the three components of the magnetic field, the BR component at the pole and the two angular component at the equator at different time, basically until 100 kilo year. We see that the solid line, again 3D, the crosses the 2D. We see that the 3D code is a bit more dissipative than the 2D code, and that's probably due, well, it's due to several reasons. One of them is that basically the two codes are different, even the coordinates are different. The second one is that the resolution in this 3D code is lower. We are restricted for the moment with lower resolution of the 3D code because the code needs to be parallelized, and otherwise it's taking a lot of time. But this difference is very acceptable, and we think this comparison is successful. Then what I have to mention is that until 10 kilo year, basically it was the Reynolds number was higher than order of unity, so it was the whole term that was dominant. So until 10 kilo year we were testing our whole term of our induction equation, and after 10 kilo year we were testing the ohmic term of our induction equation, and apparently both terms are doing well. Okay, the last thing that we want to test is that we have started in the 3D code with the axisymmetric topology, and we expect this topology to remain axisymmetric. The way to do that is to write your energy spectrum as following, and you present your energy spectrum as a function of time. As a function of the m. The m are the modes. For m equal to 0, you have the axisymmetric topology, and we see that most of the energy is at m equal to 0. But then we see these peaks which are orders of magnitude lower than the other than the main m equal to 0 peak. So basically this other peak, since they are order of magnitude lower, they don't contribute to the total energy, but we want to understand what are these peaks. So we see that most of these peaks are a multiple of 4, and these peaks are basically some error that are introduced because of our grid, because along around the equatorial belt we have these 4 patches that we saw, and these patches, since there is the interface between the patches, that kind of introduce some error to our result. Now, what we care about is that this error is small compared to the physical result, which is the case, because here is log scale and this is several order of magnitude lower. The other thing we care about is that this error should not grow in time, and if we play this evolution for 100 kilo year, we see that they are not growing in time, and I think this comparison is comparable. This test has passed successfully. Now, the last test I want to speak about is a 3D non-axisymmetric test. Is a large-scale crystal confined test. For this test, I chose a colloidal multipolar field of 10 to 13 Gauss. As I mentioned previously, for us it's very easy to construct a multipolar field because we can just sum different spherical harmonics. So I was summing from L equal 1 to 5, and I also have considered a toroidal multipolar field of 10 to 14 Gauss. My average magnetic field at time 0 was about 10 to 14 Gauss. The crystal shell was about 1 kilometer, and the average Reynolds number is 10, whereas the maximum was 200. So basically the whole term is dominant, at least at the beginning of the run. What I am showing here is a meridional cut of the B phi component of the magnetic field. So it's the cut along the meridian, and here I am showing the equatorial cut, so cutting at the equator. And now if we play this video, we see how the magnetic field is rearranged, and we see also some formation of little multiple that are directly disappearing, and that's because of the low resolution that we have. So our code cannot much handle this very small multiple at this level because it needs to be parallelized. Then in order to better understand what's going on, it's more interesting to study the energy spectrum. So here I'm showing the energy spectrum as a function of L and the energy spectrum as a function of M at different time until 20 kilo year, but the simulation is still ongoing, and I think now it have reached some 30 kilo year. At time 0 we can see the initial topology that I define, which is from L equal 1 to basically L equal 5, and we also see that it was a non-axisymmetric topology, since not only M modes are at the beginning, but there is several M higher, non-axisymmetric M, that are also excited. And then we see that as soon as we start our evolution, what happens is that the magnetic energy is redistributed over different spatial scale. The same here, so we see that the magnetic energy is transferred to higher order non-axisymmetric M modes, and then the higher multiple, they dissipate faster. And since they dissipate faster, we think that this kind of enhance the ohmic heating in our system or in our star, and that could also explain the persistent luminosity that we observe in our star. Now, having this spectral energy written in this way, one can notice that we can easily separate the poloidal and the toroidal part of our magnetic field, which is something in 3D is not so trivial, because basically our magnetic field, it mix the toroidal and poloidal component of our magnetic field, they mix. What I'm representing here is the energy spectrum as a function of L for the poloidal field in yellow and for the toroidal field in red. If we play now this video, we see that some part of it seems to be that some part of the poloidal energy is transferred to the toroidal energy, and that's probably due to the fact that initially I'm starting with the toroidal energy that's only account to some 15% of the total magnetic energy. So our system, it tends to kind of redistribute the energy between poloidal and toroidal. What the final thing I want to show is the energy as a function of time. So then the energy balance or the total energy in our system is in solid line, and we see that's a constant. So which means that even with a 3D non-axisymmetric run, our energy balance is our total energy is conserved in the system. The second thing I want to show is the divergence of the magnetic field that's orders of magnitude lower than the G2 of the star, and it's not growing in time. And finally, this is just a plot of the magnetic energy, the poloidal and the toroidal part, that we see the toroidal part, it's less than it contributes less to the total magnetic energy. Now we can summarize and understand and check what are the next steps, since this work is still in progress. So we have successfully, I think, tested both ohmic and Hall term of our induction equation. We also saw that our code conserved the total energy in the system. Our algorithm also conserved the divergence free of the magnetic field. So if we start with a magnetic field that's divergence free, our code is not making the magnetic field non-divergence free. We followed a long-term simulation up to 10 to 5 years with a strong magnetic field of the order of 10 to 14 Gauss. We saw that the magnetic energy was redistributed over different spatial scale, and we saw also that this non-axisymmetric M mode are also excited. As Stefano mentioned last week, we managed now to have a magnetothermal coupled code, but with simplified microphysics. And the next step is basically to explore more complex topology for the magnetic part, to parallelize the code, to have the magnetothermal code coupled together in 3D but with realistic microphysics. And for a future project, basically to couple the code with some realistic microphysics, some realistic boundary condition like the magnetospheric one, and also explore more the physics in the core. And thank you for your attention.
Thank you very much, Clara, for this nice presentation. We have time for questions. Please raise your hand or just switch on your camera. Okay, because people are shy, I'll have one. Mm-hmm. You have compared 3D and 2D models, and in general there seems to be an agreement, although you have shown some disagreement. Yeah, here, exactly. So my question is, so I understand that these 3D models are of course better than 2D, right? More realistic.
Yes.
So what is going to happen in the near future? So are 2D models going to become obsolete? So the community should be using these 3D ones?
Well, okay, so basically this 2D code has been developed in decade, so it have more pieces. Now, if we manage to have a 3D code that is coupled with realistic microphysics, we can study this, we can use more this 3D code. But there is some study, for example, if you want to study the luminosity, like the luminosity of a star, you probably don't need the 3D code. So there is some stuff that depends on what you want to study. For example, if you want to study a hotspot, and you know that you need the complex magnetic field to describe better this hotspot. Probably at that level you need a 3D code to better describe the evolution of the magnetic field and the formation of this hotspot in your system. But let's say you want to study luminosity in your system, probably a 2D code should also do the work. So that depends on what you want to study.
Yeah, makes sense. Okay, thank you.
Yeah. Okay.
Any other questions? Yeah, Fabio?
Yeah, hello, Clara. Thank you for a very nice talk and great results. I wanted to ask a couple of things, but rather general. Do you have an idea what would happen if you have some different boundary conditions? So in terms of allowing outflows, like things similar to stellar winds? How much you thought about that?
Okay, so basically if we couple to the magnetosphere, that means that you allow more current to circulate outside. So, well, basically there also should be some current that also coming to the star from the magnetosphere, and that could probably push more for more evolution or better, more like dynamic in your magnetic field. But if you allow to some, I think like whenever you are coupling with a magnetosphere, there probably could be some more dynamic of the magnetic field because of the current that's coming and going back from the magnetosphere to the interior of a neutron star.
Yes, and the other thing was about non-axisymmetric modes, actually, because when you have non-axisymmetric modes, it's where also more interesting things may happen.
Exactly.
So they are much more difficult to understand. Like,
yeah,
for instance, you cannot have like self-sustained magnetic fields that are completely axisymmetric. So
this is for sure.
Yeah, I don't know if you have an idea of how to go that way to understand the deviations from axisymmetric modes.
I think even, I mean, I don't think it's about only the coupling with the magnetosphere. I think even now with, if you start from non-axisymmetric topology, which is more realistic topology, we already see that these high non-axisymmetric modes are excited. Now I can tell that at the level of understanding this result, maybe I need more higher Reynolds number, something that's more gives some more dynamic in order to understand these modes that are very interesting to understand. But indeed, I would say that I still need some time in having more non-axisymmetric run that are more extreme and to understand what can be developed. It's I think, but this I mean, the magnetosphere or coupling with a magnetosphere will play an important role, but also the interior I think will play an important role as well. I don't know if you agree with me.
Yeah, absolutely. I totally agree, and I was simply wondering how to have a sense of what will happen, and you explained it, but also how to try to implement this, because it's to simulate also a magnetosphere. It's like it's a different game, and so one should try to perhaps just change the boundary conditions and
I think
the effect.
I think to couple things with the magnetosphere, one should. I mean, what we know is that the relaxation time in a magnetosphere is so fast. So basically, when you go to the magnetosphere, you need a very small time step to couple with to do the evolution in the magnetosphere, let's say. And I think if you want to do one evolution from the core, from the interior to the magnetosphere, is computationally very expensive. And what you should do instead is not doing this full evolution, but as kind of feeding results. So for example, you start doing the evolution inside your star, you reach at the boundary, at the surface, and then here you give some input to your magnetospheric code, which is what you get at the surface. This magnetospheric code should in turn return the result that is the output, because it relaxes very quickly, so it returns some output, and then you feed this output as boundary. I think doing some evolution from interior to the magnetosphere will be very expensive computationally.
Yeah.
As far as I know. But I think this should be the way. Maybe you give some interpolation, or you just give some table of number. I mean, this is the idea that I have in mind. Then it's more study, of course, is needed in order to have things working properly.
Great, thank you, and good luck for
Thank you.
follow-up works.
Thank you, Fabio. Any other questions? No. Okay, then I think we can thank Clara again. Thank you, Clara, very much. And see you all next week, still online. Thank you.